Dear students, today I am going to discuss module 4 digital signal processing. Under this module we are going to discuss about few of the problems on Chebyshev filter. So in this filter we are going to discuss the first problem. Determine the lowest order of Chebyshev filter that meets the following specification. So here you have to understand the question. Here it is given, the specification is given in dB. So if the specification is given in dB, the formula for finding the order of the filter is different. So first here the given data is 1 dB ripple in passband. Okay, that is nothing but 1 dB means the gain of the passband is 1 dB and the passband cutoff frequency is 0.3 pi, and 60 dB attenuation in stop band means the gain of the stop band is 60 dB and the cutoff frequency will be 0.35 pi. Okay, so here it is given omega 1 is the cutoff frequency of your pass band, omega 2 is the cutoff frequency of your stop band, and this alpha 1 is the gain of your pass band. So we can represent as alpha 1 or we can represent as k1, and alpha 2 is the gain of your stop band. You can represent alpha 2 or you can represent k2. If alpha 1 is equal to 1 dB, then we need to calculate the gain in terms of a1, that a1 will be is equal to 10 to the power k1 divided by 20. K1 is minus 1, so if you substitute the value of K1, then you will get the gain of the passband. The gain of the passband will be 0.891. And the similar way you need to calculate the gain of the stop band. Here they are given that you need to use bilinear transformation technique to convert the analog transfer function to digital transfer function. We are going to design the analog transfer function using the given specification. Then to convert this analog transfer function, we are going to use bilinear transformation technique. And now we have to calculate the attenuation constant, which is denoted by epsilon, and this will be is equal to 1 divided by 1 a1 square minus 1. A1 is the gain of your passband, square root or 1 by 2. So the A1 we have calculated 0.891. If you substitute, then you will get 0.509. This is the attenuation factor of your the passband gain. Now you need to calculate the analog edge frequencies. The analog edge frequency is omega 2 divided by omega 1. This analog edge frequency omega 2 will be is equal to 2 by t tan of omega 2 divided by 2, and 2 by t tan of omega 1 divided by 2. If you substitute, you will get the value 1.2. If you are keeping in radian mode, you can write the pi as such. If you are keeping in degree mode, instead of pi you should put 180. If you calculate, you will get 1.2. Now the given question, it is order of the filter you need to find. So you need to find the order of the filter where n is greater than or equal to cos h inverse of 1 by epsilon 1 by a2 square minus 1 to the power 1 by 2 divided by cos h inverse of omega 2 divided by 2. Already we have calculated this ratio, it is 1 by 2. Directly we can substitute. So here this epsilon is also already calculated, which is attenuation factor 0.509, that you can substitute directly over here. And so you have to calculate the order. So the order will be, you have to take the nearest value, which is 14. The order of the filter is 14. So this is the order of your given specification, lowest order of the Chebyshev filter. Now let us see the another problem. So see, the next problem is same. The next problem is also given in dB. So 2 dB ripple in passband, that is here you have to find the lowest order Chebyshev filter, and here 2 dB is the gain of your passband and 50 dB is your gain of your stop band. The passband frequency, cutoff frequency is 0.25 pi and the stop band cutoff frequency is 0.4 pi. And in order to find the ripple in passband, actually in order to find the gain in passband, Using the given ripple, you are going to find the gain. Gain A1 will be is equal to 10 power K1 divided by 20 is equal to 10 power minus 2 divided by 20, which is equal to 0.794. In the previous problem, we are not going to find the analog transfer function, so that what we have done, we have not calculated this A2, but here we need to do so that A2 also I am going to calculate. A2 equal to 10 power K2 divided by 20. K2 is 50. So minus 50 divided by 20, 0.0031. So these are the gain of your pass band. This A2 is the gain of your stop band. And this A1, the gain of pass band. A2 is the gain of stop band. Omega 1 is the cutoff frequency of pass band. Omega 2 is the cutoff frequency of stop band. Now here they have not mentioned which transformation technique you have to use for conversion of analog to digital. So here we are going to choose bilinear transformation technique. So attenuation factor next we need to calculate. You can use to find the attenuation factor, you can use either A1 or A2, that is pass band gain or stop band gain. So an epsilon equal to 1 by A1 square minus 1 square root divided by A1 square already we have calculated, the value is 0.794 square minus 1 square root. So the attenuation factor will be 0.765. Now next you need to calculate the edge frequency, because we are going to use the formula in the order to find the order of the filter. Omega 2 divided by omega 1 will be equal to 2 by t tan of omega 2 divided by 2, 2 by t tan of omega 1 divided by 2. Here the t is not given, means you can assume that t is equal to 1 second. Okay, if they given means you have to use that value only. If they are not mentioned the value of the sampling period, you can assume the value will be equal to 1. So after finding this one, the ratio will be 1.754. Okay, so that we are going to substitute here. Epsilon we have calculated 0.765, and the A2 here formula we can use A1 already we have calculated using A1 for epsilon. So A2 you need to calculate. So A2 already we have calculated and we kept, and the A2 value is 0.0031 already we have calculated, that we are going to substitute, and here the nearest value is 6. So the order of the filter is 6. Next, you need to calculate the cutoff frequency. To find the cutoff frequency, either you can use omega 1, that is the pass band cutoff frequency, or stop band cutoff frequency. If you are using pass band cutoff frequency, then the gain also should be pass band gain. So using that formula, we are going to find the cutoff frequency. Cutoff frequency will be equal to 0.866 radians per second. Next, you need to calculate the analog transfer function. Here the order of the filter is 6, that is order is even, so that we need to use this formula. So using this formula we are going to find the order, and here in uni, because we know that C naught is equal to omega yn, so we need to calculate first this yn value. Epsilon already we have calculated 0.765, that using that value you are going to find this yn, that is 1 by 2 1 by epsilon square plus 1 whole square root plus 1 by epsilon, order will be 1 by 6 minus 1 by epsilon square plus 1 square root plus 1 by epsilon minus 1 by n whole power minus 1 by n. So using that this formula we have calculated, this yn value is 0.13183. This yn is equal to C naught. Next you need to calculate Ck. Ck is equal to, we know the formula already we have discussed, yn square plus cos square 2k minus 1 into pi divided by 2n. 2n is 6. Next k value is C1. C1 equal to, we have to find this k value, we are going to take, assume k value is equal to 1. So C1 equal to yn square plus cos square 2 into 1 minus 1 pi divided by 2 into 6. This k value is, this C1 value is equal to 0.9664. Next B1 value is equal to 2 into yn, because you know that the order will be, what is the order? The order of the filter is n is equal to 6. So then k varies from 1 to into 2n. So using that formula we are going to use kn value. Okay. So next we are going to assume B1 equal to B2 equal to B3, and let h of a is equal to 1, because this is the order n equal to even. So I have discussed the formula. So B1, B2, B3, omega 6 equal to 1. this value b1 b2 b3 omega c square 6 divided by c. So here b1 b2 b3 omega c6 divided by c1 c2 c3 omega 6 is equal to 1. Okay, and here this b1 equal to b1 b2 b3 omega c6, this value c1 c2 c3 all values we have calculated. This if you equate this b1 b2 b3 omega c6 equal to c1 c2 c3 omega c6, that values, this value if you equate, this omega c value already we have calculated. Okay, so using that we are going to find the b1 b2 b3 value here. Now b1 b2 b3 is equal to c1 c2 c3 to the power 1 by 3, because it is we know that omega c6 we have calculated. Okay, so using that value, the c1 c2 c3 value we have calculated, we are going to substitute, and and we are going to find this b1 b2 b3 value. So already we got the cutoff frequency. Okay, using a1 and omega 1 we have calculated the cutoff frequency. Okay, so the cutoff frequency equal to 0.866. The cutoff frequency will be 0.866. That value we have to substitute, and we are using that we are going to find the value of b1 b2 b3. Now analog transfer function, the analog transfer function, we are going to substitute this all these values. Okay, so this formula already I have written. The analog transfer function HA of S is equal to b1 omega c square divided by s square plus b1 omega cs plus c1 omega c square into b2 omega c square divided by s square plus b2 omega c plus c2 omega c2 square in open the bracket b3 omega c square divided by s square plus b3 omega cs plus c3 omega c square. All the values, omega c value, b1 value, b2 value, b3 value, we are going to substitute, and yeah, we are going to find the analog transfer function. Okay, this is the analog transfer function. Now it is not given which transformation technique you need to use to convert this analog transfer function to digital transfer function, and also the sampling period also not given. So here we are going to take the sampling period equal to t1, and bilinear transformation technique already I told that we are going to use. So if you are using bilinear transformation technique, wherever s is there, there you have to replace 2 by t, 1 minus z power minus 1 divided by 1 plus z power minus 1. So here s, wherever s is there, there you are going to replace this value. Here s is there, there you are going to replace this bilinear transformation technique, that is 2 by t, 1 minus z inverse divided by 1 plus z inverse. And one more thing here, you can substitute the t value. T value will be is equal to 1. Okay, and now I'm going to take LCM. Okay, for this equation I'm going to take LCM. Now all the three things you have to substitute s value here, here, here. So now I'm going to take this equation alone and see here 2 into 1 minus z inverse divided by 1 plus z inverse whole square plus 0.081 into 2 1 minus z inverse divided by 1 plus z inverse plus 0.724. I'm going to take LCM. If you are going to write here 2 square 1 minus z power minus 1 whole square divided by 1 plus z power minus 1 whole square. So if you take LCM, this will be 1 plus z power minus 1 whole square. Here 4 into 1 minus z power minus 1 whole square. It will because already 1 plus z power minus 1 whole square is there, so we are not going to write, plus 0.081 into 2 1 minus z inverse into 1 plus z inverse plus 0.72 into 1 plus z inverse to the power 2. So for all the value I am going to substitute. After substituting this and simplifying the denominator equation, all the three equations you need to simplify. All the equation you need to simplify. So after simplifying this, you will get 0.278 1 plus z power minus 1 whole square divided by 4.886. See this one, you need to simplify all the equation, and finally all the denominator, this denominator equation will be 1 plus z power minus 1 whole square will goes to numerator. So this is your digital transfer functions. Okay, this is your digital transfer function for the given specification using bilinear transformation technique. Thank you, students.